So let's look at some interesting examples here. So a little bit more of a refresher on partial derivatives. So let's say we had something like f of xy equal to e to the negative x squared times sine of x to the fourth plus y to the third. We want to find our first partials because, well, let's find the first partials and we'll talk about whether finding the second partial seems like a good idea or not. So let's go ahead and find the first partial with respect to x first. I don't care which way you write it. You can write it as del f del x. You can write it as fx. This means we're taking the derivative with respect to x. So as far as this is concerned, we have e to the negative x squared times sine of x to the fourth plus a constant as far as this partial derivative is concerned. And unfortunately, that means we're going to have to use the product rule because we have a function of x times another function of x. So you don't need to do this next part, but if you want to, you can think of like, you can call this function u and this function v. And then just remind yourselves, we're doing the derivative of u times v plus u times the derivative of v. So our fx, the derivative of u is going to be, okay, chain rule, the derivative of e to the stuff is e to the stuff times the derivative of that stuff. That's my u prime. And then I'm going to leave the v alone. So we're going to multiply that by sine of x to the fourth plus y cubed. That's my v left untouched. Plus, then we switch it. We leave u alone. So it's going to be e to the negative x squared, just good old u, unchanged. And then the derivative of v is going to be, well, the derivative of sine of something is going to be cosine of that thing. And then we have to multiply by the derivative of the inside. Now, this is where we actually have to pay a little bit closer attention. The derivative of x to the fourth plus y cubed with respect to x, aka treating y as a constant. The derivative of x to the fourth is 4x cubed, and the derivative of y to the third is 0. So there go del f del x. Why don't you all find del f del y, which is going to be a lot less terrible because you do not need to use the product rule to find it. I'll give you a minute. Thanks, appreciate it. So to find the partial derivative with respect to y, similar process, right? We're going to treat x as a constant. So this e to the negative x squared out in front here is a constant multiple as far as we're concerned. So when we take the derivative of e to the negative x squared times sine of some stuff with y in it, the e to the negative x squared multiple is just going to stick around. And we're going to multiply that by the derivative of sine of whatever. So that's going to be cosine of x to the fourth plus y cubed multiplied by the derivative of the inside, which is 0 plus 3y squared. That's it. These ones look gnarly enough that I don't think we should, especially, yeah, we should not find any second partials here because it's kind of gross. But we could. But I think it would be an exercise in self-hate if we did that. So we will not do that here. We'll do another example though. I feel like so are any questions about what we've done here before we move on to another example? So I make sure it's super clear. The reason we're leaving this e to the negative x squared in front here is because if we had something like, if you had a function f of x equal to 7 times sine of, let's say f of y actually. 7 times sine of 2 to the fourth plus y cubed, that multiple 7 would just hang out when we take the derivative. And your derivative f prime of y would be 7 times cosine of the inside stuff left alone. And then you multiply by the derivative, and the derivative of 2 to the fourth is 0, and the derivative of y cubed is 3y squared. So as I've said a few times, constant multiples hang out, constant on their own end up having a derivative that's 0. Interesting. So there is something else I want to mention that's related to this, but it's a little bit different. So let's say we had something like the following. So let's say we have not a function, but an equation. Let's say we have x squared plus y cubed plus 2z to the fourth equal to x times y times z. And we're asked to find fx, fy, and fz. I'm sorry, so, that is not what I meant to say at all. Apologies. Scratch that. Sound like you never saw it. What I meant to say is we want to find del z del x. And this is an example of partial derivatives with implicit differentiation. So just like back in 17a, when you had like an equation with x's and y's mixed up together, and they said find the derivative of dy dx using implicit differentiation, we pretended like y was a function of x, even though it might not have actually been. We're going to do the same thing here. If they ask us to find del z del x, we're pretending like which variable is the function, x, y, or z. Right, the one on top, the z. So we're pretending like z is the function, and we're pretending like x is the variable, and y. But if we're finding del z del x, it means we're differentiating with respect to x, and we're pretending like y is a constant, and z is the function. So here, we're going to do like we did back in the day. We're going to take the derivative of both sides with respect to x. So the derivative of x squared is going to be 2x. The derivative of y cubed is going to be 0. Here's where it's going to be a little bit weird. The derivative of 2z to the fourth is going to be 8z cubed times del z del x. Because again, we're imagining that z is the function. So z is some function of x, and when you take the derivative of 2 times something to the fourth, we have to use the chain rule. So we're going to get 2 times 4 times z cubed multiplied by the derivative of the inside thing that was raised to the fourth power, which is where your del z del x is actually going to show up, equal to the derivative of the right-hand side. So for x times y times z, we're going to have to use the product rule. So I would probably, how would I think about this actually? I would probably think of this, since y is acting like a constant at this moment, I'd probably think of it as xy times z. So it's a product of two things. The derivative of xy is going to be 1 times y. And then we're going to leave the z alone, right? Because that's how the product rule works. You take the derivative of one part, you leave the other part alone, and then you switch it up. We add, we're going to leave the xy alone. And now here's the sometimes challenging question. What's the derivative of z? Well, I already said the answer. It's right, it's the derivative of z. Although, except this time it's actually del z del x because z is a function, or we're pretending like z is a function of more than one variable, so it's a partial derivative. But yes, the right idea. Del z del x. After this, the rest of the process is the algebra. So we have to collect all our del z del x terms on one side, everything else on the other side, factor, divide, etc. So I want this term and this term on the left. So I'm going to have 8z cubed, right? Because 2 times 4 is 8, times del z del x minus xy times del z del x equal to 1 times y times z minus the 2x. We're going to factor out the del z del x on the left. So we have del z del x times 8z cubed minus xy equal to still yz minus 2x. Important note here, especially for myself, make sure your z's and your 2's look different. Sometimes my z's and my 2's start to look the same, so make sure your z's look different than your 2's. I usually put a little horizontal line on my z's like that. And then finally, divide both sides by 8z cubed minus xy to get del z del x equal to yz minus 2x divided by 8z cubed minus xy. The reason I'm actually giving you this example right now is because a little in the future, after we've talked about the chain rule for functions of two or more variables, we'll see an easier way of calculating this derivative instead of using implicit differentiation. So we'll come back to this example or a similar example and talk about, oh yeah, there's this kind of slick way of doing this, which works every time. Um, I would say on your own, when you have a moment, I would encourage you to find del z del y. But you don't have to do that right now. I want to move on, but maybe we'll come back to that if we have time. There's always so much to say. Okay, got to keep things in order. It's a problem with so many papers up here is everything gets out of order. So one more partial derivative idea, because I do want to say one more thing. Yeah.
Like 1 times y c. What happens?
It's right there.
1 times c.
Well, so when you multiply, what's 1 times y?
Uh,
Right. So then I just have y times z, which is y times z. But what I think you're asking, I just want to make sure. So like, for example, if I had say like 2 times y times z, we don't have any sort of distributive property here. It's just 2yz. So just want to make that really clear. If it was 2 times parentheses y plus z, then the two would distribute across the addition. Cool. So let's do one more thing here. Let's say we have something like, sure, oh yeah, this will be interesting. F of xy equal to y to the fifth power times 8x minus 3y squared. And we are asked to find del squared f del y squared. The purpose here really is to understand that we can make our lives easier. We don't have to use the product rule here. In fact, well, no, that's true. We do not have to use the product rule, and we shouldn't. We should multiply this out first. So as was true in 17a and 17b, if you can make something easier by simplifying it first, that's usually a good idea. So here, before I do anything, I'm going to say, well, my function, f of x comma y, is going to be y to the fifth times 8x, or 8xy to the fifth, minus y to the fifth times 3y squared, which is 3 times y to the seventh. And then taking the derivative is not too terrible. My first partial derivative, del f del y, is going to be this 8x is going to hang out. The derivative of y to the fifth is 5y to the fourth. Minus the derivative of 3y to the seventh is 21y to the sixth. And I definitely should do myself the favor of simplifying this a little bit before I go on. Saying 8 times 5 is 40. I have 40x y to the fourth minus 21y to the sixth. Okay, why don't you all do the next part? Find the derivative of that with respect to y. So find your del squared f del y squared. Should not be too terrible at all. You don't have to do the simplification with the multiplication. Like you can just leave it as like 40 times 4 or 21 times 6 if that's easier to do. Which you totally could do if you had to enter something like this in web work, right? If you didn't want to like mentally calculate 21 times 6, you just be like, right, 21 times 6 times y to the whatever. So there's my very acceptable second partial derivative with respect to y. 40x times 4y cubed minus 21 times 6y to the fifth. But if we wanted to simplify it, it would be 160 xy cubed minus 126 y to the fifth. Yeah. So before we start talking about tangent planes, I should pause and ask, are there any other kind of broad questions about partial derivatives or specific questions about partial derivatives? I'm kind of looking at your next homework assignment that's not posted yet, homework number two. Do you guys know you can access the homeworks like ahead of time? Well, I don't, I should take that back. You might be able to. Maybe it's just me. I might be able to because I have access to your Canvas and I probably have like a teacher privilege. But I have noticed that if you click on homework one and then make it load, and like I like to print them out. So you go like you hit the little button like to print the PDF. Over on the right hand side, there's like homework one, homework two, homework three, homework four. So if that's over there for you, you might be able to like see homework two early if you wanted to. I don't know if you can actually do that, but you might as well take a look. Anyway, that's what I was doing today because I was like, oh, I want to see homework two and it's not available yet. So I should remember the trick I had. So anyway, I'm looking at problems from homework two and they're kind of like this. Yeah. So, yeah. Let's go ahead and talk about tangent planes and linearizations, which are kind of the same-ish thing. They're not exactly the same, but they're pretty much the same. As always, you're welcome to ask questions. But if you don't, I'll just keep on talking, which is totally fine. So tangent planes, linearizations. So this is one of the examples of a topic where we kind of did almost exactly this in 17A. And all we're going to do now is extend this idea by kind of just adding on an extra piece. Let me say more about that. So, oh man, I've been a little kind of sort of coffee today. So, reminder, in 17A, the equation of a tangent line, sorry, I should say the tangent line, not a tangent line, the tangent line to the function y equals f of x at the point x naught comma y naught. Well, typical equation of a line, y minus the y coordinate equals your slope times x minus the x coordinates. But we're going to write it this way. We're going to write it as y minus y naught equals f prime of x naught times x minus x naught. There's your y coordinate. There's your slope. There's your x coordinate. Now, when we did linearizations, well, I should say, when you do a, sorry. When you do a linearization, you're typically isolating y. You're expressing y as a function of x. So we want it to be by itself. So we usually would write this as a linearization. And for whatever reason, when we write it as a linearization, at least in 17a, we typically would use a and f of a instead of x naught and y naught. So we can use x naught and y naught. We can also use a and f of a. Same idea. It's just an x coordinate and a y coordinate. So then we would say y equals, we bring the y naught over to the right-hand side, but it's your f of a now, and it's the slope f prime of a times x minus the x coordinate, which is x minus a. And I should have called this L of x. L of x equals f of a plus f prime of a times x minus a. That's your linearization of the function at the point a comma f of a. All it is the equation of the tangent line. Right, that's all linearization is. It's the linear thing that's tangent to your stuff at your point, whether your stuff is a line or your stuff is a surface. Let's look at one example, just to kind of remind ourselves. And I should not try to squeeze anything on this page. Learn my lesson, hopefully. So let's do the following. Let's find the linearization of f of x equal to the square root of x at a equal to 9, and then use it to approximate or estimate the square root of 8. Okay, so graphically, here's what's happening. And again, I know this is something we've done before, so I kind of remind you because it's easier to draw for a line than it is for a surface. And the idea definitely is easy to imagine, but hard to draw in 3 dimensions. So we've got our function f of x equal to the square root of x. And we're almost always trying to linearize a thing at a convenient point. Right? The reason I'm picking 9 is because 9 is easy to plug into the square root function and get a nice output. So whenever you're trying to pick a point that didn't give you the point to do the linearization at, you're thinking, I should be picking something that's easy to plug into this function and easy to compute what's coming out. So graphically, what's happening here is we're saying, right on, here's my point, my x value, my a value 9, and we're just going up to the function, and we're finding the equation of this tangent line. So this line here, that is our L of x. Our function is the square root of x. Our function evaluated at the nice value a is f of 9, which is the square root of 9, which is 3. We need the derivative to get the slope. The derivative of the square root of x, or x to the 1/2, is 1/2 x to the negative 1/2. Or as you will often see people write it, 1/2 root x. Same thing, just a different way of writing it. And if I plug in 9, my f prime of a is 1/2 times the square root of 9, which is 1/2 times 3, which is 1/6. So the slope of this line is 1/6, which seems plausible by that slope, certainly the way I've drawn it, and I've drawn it decently enough. It looks like you could be going over 6 and up 1 on that line. So our linearization is equal to our, I almost always write it again, but can you see it up there? No, you can't. Let's see, our linearization right there. It's f of a, so it's going to be 3 plus f prime of a, 1/6, times x minus a, and a is 9. Okay, something worth mentioning. It is rarely in your interest to simplify this at all. When you have a linearization, you almost always want to leave it as something plus your slope times x minus whatever. Because usually the thing you plug in to estimate this is going to be very close to the thing you're subtracting here. So this part's going to become small. It should be, I think, somewhat obvious is not the right word, but it shouldn't be hard to see here that if we estimate the square root of 8, it shouldn't be too far from 3. Right? The square root of 9 is 3. If you change your input just a little bit, the square root of something close to that should be still close to 3. At least if your function's continuous, it doesn't have like wild behavior. So how are we going to estimate the square root of 8? Well, I should have pointed out this linearization here is an approximation of our function. Right? The square root function is close to this line as long as your input is close to 9. If you move too far away, these are going to get further and further apart from each other. But as long as we're close to 9, and close is one of those words that, depending on the context, can be, within decimals or within thousands, depending on what we're talking about and how big your kind of scale is. But here, what we're going to say is, cool, the square root of x is approximately the linearization of x, which is this. So then we're just going to substitute in 8 for x and say the square root of 8 is approximately L of 8, which is 3 plus 1/6 times 8 minus 9, which just ends up being 3 minus 1/6, which you could write as a fraction, although I find it less helpful usually. That's 18/6 minus 1/6, which is 17/6. Usually I would prefer this, but in this context, if I'm going to compare it to like something I would get on a calculator, it actually feels more helpful to like write it as a decimal. So 3 minus 1/6 is 3 minus 1/6 is 0.1666 forever. So it's like 2.833 forever. And if you look at the square root of 2, it's like 2.82. So pretty close, right? Not a bad estimate for just drawing a line and doing a thing. Okay, so the good news is tangent planes and linearizations and for functions of two variables has essentially the same like format. We're going to write almost the same thing. We're just going to tack on an extra piece. So let's look at the actual thing we're trying to talk about here. Let's see. So now in 3 dimensions, we modify just a little bit. So here's what our tangent plane equation is going to look like. So let's write it. We're going to find the tangent plane to, instead of the tangent line to a curve, it's the tangent plane to a surface. You might imagine like, surfaces are always hard for me to imagine. Like the surface I always go to is a sphere. Like you might imagine, oh, in fact, yeah, it's kind of spherical. You might imagine you have an orange and you pick a point and then you draw the tangent plane at that point. Like that, kind of, except the paper should be straight like that, right? There's your tangent plane to the point on your surface. So the way we're going to do that is to the surface. We're thinking of the surface as z equal to f of xy at the point x naught, y naught, z naught. Okay, let's pull up that. Oh, I'm getting papers all out of order here. So really, I'm just going to look at this thing we did over here. Let me move. Sorry, I'm getting all things out of order now. I'm just looking at this equation here. This y minus y naught equals f prime to x minus x naught. And we do the same sort of thing. It's going to be z minus z naught equal to, instead of just f prime, it's going to be the partial in the x direction. So the partial derivative with respect to x evaluated at x naught comma y naught, because you have to have the slope at the point, times x minus x naught. And then we're just going to do the same exact thing, but for y instead of for x. So the second part here, which we're kind of adding on, is the partial with respect to y evaluated at x naught comma y naught times y minus y naught. Practically the same equation. And then the linearization is not that much different. You just isolate z and call it L of x, y. So our linearization is going to be L of x, y. And instead of writing z naught, we write it as f of x naught, y naught. Because z naught is what you get when you plug in x naught and y naught to your function. So it's going to be L of x, y. Do I have enough room? Hopefully. It's f of x naught comma y naught plus all this stuff we just wrote. Fx. So just for your edification, sometimes people write this, instead of writing fx parentheses x naught y naught, they write a vertical line and then the x naught y naught down here. Because it like takes up less room in some way. So it's fx evaluated at x naught y naught times x minus x naught plus fy evaluated at x naught y naught times y minus y naught. And just so everyone's clear, this L of xy is just your, now that's actually your linearization. It's what we're saying. It's kind of what we're replacing z with. We're replacing z here. Replacing z equal to f of xy with the thing it's approximately equal to. But this f of x naught y naught is actually what your z naught value is. So the equation is really not that terrible if you remember the equation from 17a. It's really the same idea. So now we can answer some questions. Okay, so let's look at some examples. So where'd you go here? Yeah. Let's find the linearization of f of x comma y equal to x to the fourth times y cubed at the point -1 comma 2. And use it to estimate f of -0.9 comma 2.2. So I'll point out sometimes, less so in this class, but still occasionally, they might have left off the where you're finding the linearization at. They might have just said, use a linearization to estimate f of negative 0.9 comma 2.2. And then it's your job to know, oh, I should be doing that linearization at negative 1 comma 2, because those are the closest nice points that are easy to plug into the function. So that's something we should kind of think about. Like, what are the nice points that are closest to the things we're actually trying to estimate it at? All right, so typical deal here. We're going to find our partial derivatives. So we're going to say that, sure, fine. I'll write my function first. So f of x, y is x to the fourth times y cubed. My partial with respect to x is 4x cubed times y cubed. My partial with respect to y is x to the fourth times 3y squared, which I don't feel compelled to put 3 in front. And then we're going to want to plug in our nice point into each of these pieces. So this is going to tell us that our z naught, which is f of x naught y naught, is f of negative 1 comma 2. And we're just plugging that in. So we're going to get negative 1 to the fourth times 2 cubed, which is 8. Here, our fx at negative 1 comma 2 is going to be 4 times negative 1 cubed times 2 cubed, which is going to be 4 times negative 1 times 8, which is negative 32. When you look at this part here, you should be thinking, okay, that's the slope in the x direction. It's pretty steep, right? So if you're on this surface at this point and you move in the x direction, it's like going way downhill real fast. And then our fy is evaluated at negative 1, 2 is going to be negative 1 to the fourth times 3 times 2 squared, which is 1 times 3 times 4, which is 12. So on the other hand, if you move in the y direction, so I should point out, when I say move in the x direction, move in the y direction, specifically we're moving in the positive x direction and the positive y direction. So I move from left to right in the positive y direction, right? Because we're thinking your usual three-dimensional setup, our slope is positive 12. If I move back to front in the positive x direction, my slope is negative 32. The interesting thing about that, and this is going to come up when we start talking about directional derivatives, is if you move in the opposite direction, your slope is kind of the opposite value, right? If I move in the negative x direction, my slope is actually positive 32. If I move in the negative y direction, my slope is actually negative 12. All right, so then we just put it all together. So we're just going to use this formula and say my linearization of x comma y is equal to my f of x naught y naught, which was 8, plus my fx, which is negative 32, times x minus the x coordinate, which is negative 1, plus my fy, which is positive 12, times y minus the y coordinate, which is y minus 2. And as I mentioned before, it is almost never a good idea to simplify. Okay, there's one simplification you might do. You might rewrite x minus minus 1 as x plus 1. But other than that, you should not distribute the negative 32 or the 12 or do anything really. And again, we're imagining that our function f of xy is being approximated by this linearization. Okay, so now to fully answer the question, we're going to then estimate f of negative 0.9 comma 2.2 by just plugging those values into the linearization and seeing what we get. So our f of negative 0.9 comma 2.2 is approximately equal to L of negative 0.9 comma 2.2, which is going to be 8 plus negative 32 times negative 0.9 plus 1 plus 12 times 2.2 minus 2. And now we can see that, oh yeah, the math isn't so terrible here. We're going to get 8, and then we have negative 32 times positive 0.1, which is just going to be 3.2. And we have 12 times 0.2, which is going to be 2.4. That's not too bad. So then you got 8 minus 3.2 is 4.8, plus 2.4 is 7.2. I do sometimes like to check to see like how close is it actually to the value. So if you actually take out your calculator and plug in these numbers to that function, let's see. So if I do negative 0.9, I really don't need the negative here. Sure, just 0.9 to the fourth, multiplied by 2.2 to the third. 6.98, not too far from 7.2. I think it's more interesting. So I'll write this. So note f of negative 0.9 comma 2.2 is actually equal to 6.98615. Okay, we don't really care about all that. What's more interesting is, well, actually, I was going to look at the graph here real quick. So let me real quick here see if this is good looking or terrible looking. Eh, it's not the best. So here's what our surface looks like. Okay, it's kind of wonky. But let's go ahead and plot the point of tangency, which is the point negative 1, comma 2, comma 8. Oh, it might be kind of off this chart here. Let's see. Negative 1, comma 2, comma 8. Yeah, we're gonna have to zoom out a little bit here. So there's the point of tangency to the surface, right? You can kind of see it right there, just chilling. And then we're gonna draw the tangent plane. So our tangent plane or linearization was z equal to, right, I'm replacing the L of xy with z equal to 8 minus 32 times x plus 1. Whoops, not that. Plus 12 times y minus 2. And although it's not super easy to see, I think you can kind of see there that, oh yeah, that plane is definitely just touching that surface at that point, and it is tangent. Now the surface is very kind of steep, so it kind of looks like the plane's going through the surface as well, but that's not the point. The point is that right at that point, you've got some tangency going on. So kind of neat. I know I've said it before, I'm going to say it again. I highly recommend playing around with Desmos 3D a little bit at least, just to see how some of these things kind of look. It's not a bad idea. You've got all these tools at your disposal. You should use them. All right. So let's see, what else do I have on deck here? Sure. Let's do a couple more. Papers. So let's look at the following. Then we'll do an application. Let's find the equation of the tangent plane to the function z equal to 4x squared minus y squared plus 2y at the point negative 1, comma 2, comma 4. And if you prefer, you could certainly write the z part here, right? You could instead write that as f of xy if you prefer. So I want you all to try this one on your own. So I'll remind you of, I won't remind you, maybe I will. I'll remind you of your tangent plane equation right there. So I want you to find all the pieces you need. So you're going to need the partial with respect to x, the partial with respect to y. Yeah. All right, let's take a look. So I need some partial derivatives. They're not too terrible. My fx or my zx, whatever you want to call it. My fx is going to be 8x minus 0 plus 0. My fy is going to be 0 minus 2y plus 2. So then if I'm calculating these things, my f of negative 1, 2. So I'll point out the f of negative 1, 2 here. We didn't even really have to think about calculating. We already should know it's 4 because they're telling you that when you plug in negative 1 for x and 2 for y, you're getting 4 for z. But we can also check. If you plug in negative 1 for x and 2 for y, you get 4 minus 4 plus 4, which is 4. That's definitely equal to 4. Fx at negative 1, 2, well, if I plug in negative 1 for x and 2 for none of the y's that are there, we're going to get negative 8. My fy evaluated at negative 1 comma 2 is going to be negative 2 times 2 plus 2 is going to be negative 4 plus 2, which is negative 2. So those are all the building blocks we need. Now we're going to say that our equation is going to be z minus my f of negative 1, 2, which is 4, equal to my fx, which is negative 8, multiplied by x plus 1, or x minus minus 1, plus my fy, which is negative 2. I probably should have just written minus, oh well, times y minus 2. That's the equation of change plane. You certainly could isolate z here. You don't have to, though. It's totally fine to leave it as z minus 4, unless someone says you shouldn't. Z minus 4 equal to negative 8 times x plus 1 plus negative 2 times y minus 2. This one, I would probably actually simplify things because they get nice. So I would point out here we're not being asked to do any approximating. And if I'm just trying to write the equation of a plane, I might go ahead and write it more like z minus 4 equals negative 8x minus 8 minus 2y plus 4. And then bring everything to the left side and write it as 8x plus 2y plus z minus 4 plus 8 minus 4. Does it really add that plus 0, so it equals 0. So that's, in this case, probably not a bad idea. But generally, no one really cares if you simplify it or not. All right. Could look at one more example. This other example is really gross, though. I feel like we don't need to look at that one. I have one more example of this, but it's really, really gnarly. I think I'm going to skip it. Okay. So that's pretty much all there is to tangent planes and linearizations. I will point out, I'm looking at the second homework assignment. One of the things I was saying before definitely is the thing. So just to show you all, here's problem 19 from homework number 2, just so you all can see it. It says let me look. No, they're definitely not giving you anything. Okay, yeah, that's what I thought. So I feel like it says use the linear approximation or use a linear approximation to estimate 1.01 squared times 2.99 squared. So your job first is to identify the function that we'd be using. I'd probably say it's x squared times y squared. And then the nice value that we should be using for x and y is obviously 1 and 3, the values that are close to 1.01 and 2.99. I will also point out this question additionally asks you to find the percentage error. So the way you're going to calculate the percentage error is it's going to be, we should probably just do an example. Let's do that instead. Let's do something like that. Because I never remember how to calculate percentage error, and I feel like I often screw it up. It shouldn't be that hard, but let's do that. So let's say we're given a question like use a linearization to estimate, make it a little bit more interesting, 1.02 cubed times 3.99 squared. Okay, we can do that. So first, let's come up with our function. Our function, I think, should be x cubed times y squared. Although you could certainly write it as y cubed times x squared. It doesn't really matter which part's playing the role of x or y. But they do have to be different, right? You can't be x cubed times x squared because you have different inputs for the x and y value. And we are linearizing, I should say, we're going to linearize this function that we just made up at the point 1, 4, because that is the nice value we're going to plug in. And then the usual stuff, we're going to find our function evaluated at that point. So f of 1 comma 4 is going to be 1 cubed times 4 squared, which is 16. We should find our partial derivatives. Fx is equal to 3x squared times y squared. Fy is equal to x cubed times 2y, which is 2x cubed times y. So then our fx evaluated at 1 comma 4 is going to be 3 times 1 squared times 4 squared, which is 3 times 16, which is 48. Our fy evaluated at 1, 4 is going to be 2 times 1 cubed times 4, which is 8. And so our linearization is going to look like L of xy equal to our f of x naught y naught, which is 16, plus our fx, which is 48, times x minus the nice x value of 1, plus our fy, which is 8, times y minus the nice y value of 4. And then we're going to plug in the not as nice numbers to get our estimate of the value. So we're going to say that f of 1.02 comma 3.99 is going to be nicely approximated by L of 1.02 comma 3.99, which is going to be 16 plus, okay, let's not write all the things. Instead of writing 48 times 1.02 minus 1, let's just write 48 times 0.02, and 8 times 3.99 minus 4 is negative 0.01. So that's going to look like 16 plus 48 times 2 is 96. So 48 times 0.02 is 0.96. And 8 times negative 0.01 is negative 0.08. So it looks like we're getting 16. We're adding 0.96. We're subtracting 0.08. So it's 16.88. So now the question is, the question is, good question. Oh, compare with the value given by a calculator and compute the percentage error. So we use a calculator to compute this. Our 1.02 cubed times our 3.99 squared is, let's say it's 16.8945. So f of 1.02 comma 3.99 is, I know it's not actually equal to, but I'm using the equal sign to differentiate between that there. It's 16.8945. So then the percentage error is the error divided by the original value. So your percentage error is going to be the change in your function value divided by your function value. It's not technically times 100, right? If this will be a decimal, and then you multiply that decimal by 100 to get the percentage error. But okay, sure. So let's see. Our delta f is going to be, doesn't really matter which order you subtract it because you're going to throw an absolute value around it. So it's the absolute value of 16.8945 minus 16.88 divided by, you divide by the nicer value, even though that's the one that's the estimate. It's generally the practice anyway. So here we're getting, yeesh, 0.0145 divided by 16.88. That's going to be a real small. So I'm getting 0.000859 approximately. Or as a percentage, move that decimal over 2 places, 0.0859%. So I want to be super clear here, not 8%, 0.08% or 0.08%. So a very good estimate. Our percentage error is very, very small. All right. Enough of that. Move on to that. So the next topic for conversation, oh my gosh, if I can pick up these papers here. The next topic for conversation is the chain rule. Although not the chain rule I mean, yes, the chain rule you're thinking of, but not the chain rule you're thinking of. I'm happy to clarify anything from my calculator. I did, yeah, as the homework problem that I was kind of mimicking instructed me to do. Right, the homework problem said somewhere, wherever I put it, said compare this with the value given by a calculator and compute the percentage error. So I found my estimate, 16.88. I plugged in the numbers to the calculator and got 16.8945. Right. And again, it's not exactly correct because I didn't include all the decimals, but close enough. And then I took their difference from the actual versus my estimate and then divided by the estimate of the actual is typically what you do. Although I suppose you can go either way. All right. So let's move along and talk about the chain rule for multivariable functions. We'll start off with an example, which the numbers are not great, but the idea is, I think, fairly accessible. So let's talk about pressure, volume, and temperature. Some chemistry stuff that I don't know a whole lot about. So the pressure, P, measured in kilopascals, kPa. I'm not sure how you're supposed to write that, whatever. Volume, V, measured in liters. And temperature, capital T, measured in Kelvin or degrees Kelvin. Okay. If any of you take chemistry, you know what I'm about to say probably. Of 1 mole of an ideal gas are related by the ideal gas law, which is, I think it's PV equals nRT, but we have N and R, so we have P times V equals the quantity nR, which is 8.31 in this context, times the temperature T. So now here's the part that's actually important. If the temperature of the gas is 300 degrees Kelvin and is increasing at a rate of 0.1 kelvins per second, and the volume of the gas is 100 liters, seems like a lot of gas, and increasing at a rate of 0.2 liters per second, how fast is the pressure changing? Not better question. Maybe a more accessible question is the pressure increasing or decreasing? We don't know yet, right? Because if the volume is increasing and the temperature is increasing, the pressure might need to be increasing to keep up with how fast the temperature is increasing, or it might need to be decreasing because the volume is increasing fast enough to kind of overcome how fast temperature is increasing. So we really don't know. So here's the idea. First and foremost, we want to try to isolate the thing we're looking at. So instead of writing this equation as PV equal to 8.31 T, we're first going to isolate the pressure because that's what we're asking the question about. So we're going to first rewrite our equation as P equal to 8.31 T divided by V, or it might be more convenient to write it as 8.31 times T times V to the negative 1 if we're going to be taking some derivatives here. I'll point out that P, pressure, in this context is a function of temperature and volume, and it's equal to 8.31 times T times V to the negative 1. So here's the idea, and this idea is going to hold a lot of the time for what we're about to do. P is a function of T and V, but both V and T are functions of time, right? We were told volume is increasing at 0.2 liters per second, and temperature is increasing at 0.1 degrees per second. So those are both functions of time. You could literally write like V of t, V of little t equals 0.2 times t, and t of little t equals 0.1 times t. We don't need to do that though. Here's what we do. Oh, and then, well, let's just make sure I'm not missing anything here. Yeah. So we're going to model this with a mapping. And this mapping is the part that we really need to kind of be aware of. So we're going to map. Oh, wow. Can I write the word more clearly? We will map P as a function of both volume and time, and also volume and time as functions of, sorry, volume. This is it's a problem with temperature and time. They both start with T. So pressure as a function of volume and temperature. I might have said time. I apologize. And then volume and temperature as functions of time. So typically you start from the top. So pressure at the top is a function of some stuff. It immediately is dependent on volume and temperature, but then volume and temperature both are dependent on time. It's a very typical diagram for taking the chain rule for or using the chain rule to find the derivative, etc. So what's the question asking us? I know it's been like it feels like forever since we talked about the so back to the question. The question was asking us how fast is the pressure changing? In other words, what's the rate of change of the pressure? Or in other words, what's the derivative of the pressure with respect to time? So we're asking the question, what is dp dt? And yes, I do mean d here because at the very lowest level, pressure depends on the single thing, the single variable time. So big picture, pressure is a function of one variable, and we're taking an actual derivative, not a partial derivative. But to get there, we need to kind of follow every path that gets us from pressure to time. There's two paths. You either go through volume and then to time, or go through temperature and then to time. So to go from pressure to volume, we're going to take the partial derivative. It's going to be del P del V multiplied by the derivative of volume with respect to time, which is dV dt, plus the other pathway that gets us there. Del P del T, I should say del capital T times d capital T dt. The del's and d's are correct and specific. Del, when it's a partial derivative, right? We do del P del V and del P del T because P depends on V and T. But then we do dV dt and dt dt because V and T are both only dependent on time. And although I'm being very specific because I think it's important to be correct, no one cares. No one's looking to see if your del is a D or your D is a del. So just write it amorphous enough that no one can tell the difference and you'll be fine. Kind of like you're at that T that looks like an F if it's a true false question. No, but the del and the D, right? No one's looking. If you're writing it, they know you're taking a derivative. You probably know if you're taking a partial derivative or an actual derivative because you're doing it. All right, so still need this paper here. So let's go ahead and remember we've got P equal to this. So, oh, I know what I was going to say. So one thing to be aware of here is much like the chain rule back in 17a, when you write it using this notation, not that we usually do, it kind of looks like the stuff would cancel and give you what you wanted. Like here, if you multiplied this thing that isn't a fraction but looks like a fraction times this other thing that looks like a fraction but isn't a fraction, you can imagine the dv's and the del v's canceling and being left with del p over dt. Same deal here. You can think of the d capital T's canceling and being left with del p over dt. So that's kind of how you should think about it. You should think of the things, if you were to cancel them, you should be left with the derivative you're looking for. I recognize there's two of them added together. We don't worry about that. So I just moved the thing. Sorry. I wanted that there still. We're taking a derivative. So our del P del V is the partial derivative with respect to V. So it's going to be 8.31t times negative V to the negative 2. Our dV/dt, they told us in the problem. dV/dt is the rate of change of the volume, which was 0.2 liters per second. I'm not going to include the units because it's a pain to write that, but we know they're there. We'll include them at the end. Over here, our del P del T is going to be 8.31 times 1 times V to the negative 1. Multiplied by dt dt, which was the rate of change of the temperature, which was 0.1 kelvins per second. And then we're going to plug in the values we know, right? We were told in this problem that the volume was 100 liters at the moment we're looking at, and the temperature was 300 degrees Kelvin at the moment we're looking at. So we're going to get, and again, this is where the numbers are awful, but hopefully the idea is not too awful. The numbers are going to be 8.31 times 300 degrees Kelvin times, I'm going to rewrite this as negative 1 over 100 liters squared times 0.2 plus 8.31 divided by 100 liters multiplied by 0.1 liters per second. Uh, degrees per second. I'm not trying to split the units here, but the units, if you thought about the units enough, they should come out to be the same. You should end up with pressure per, or the rate of change of pressure per second. But this is a math class. We don't worry about the units. It's not true. We do sometimes. Sometimes unit analysis or dimensional analysis is actually really helpful in figuring out like how things are supposed to work. We're not going to sweat it here. So this ends up equaling, what do we get here? We get approximately negative 0.04155. This is definitely not something you should try to write. This is calculator for sure. Kilopascals per second. Or in other words, if temperature and volume are what they were and changing at the rates they're changing at, then the pressure has to be decreasing at 0.04155 kilopascals per second. Or you could alternatively say it is increasing at negative 0.4 or whatever kilopascals per second. Usually we say decreasing, but yeah. All right, so that's the broad idea, is that when you have a function of some things and then those things are functions of other things, you can make this mapping and then kind of find all the paths that get you from the thing you're taking the derivative of down to the variable you're taking the derivative with respect to. That's kind of the whole deal. Let's look at some more examples. I will point out this process is meant to save you time and effort. Right? It doesn't look like it, and especially with I know that example, the numbers are not nice, but this next example, the numbers are nice. In fact, I don't think we're plugging in any numbers actually, but I'm going to show you how it can be awful. Just so you can see, oh yeah, this really is a good thing we are doing. So let's look at this example. Suppose our function of x and y is x squared times e to the 3y. And we're also told that x is equal to cosine of t and y is equal to sine of t. And we are asked to find the derivative of f with respect to t. And we're going to do this two different ways. First, the hard way. First, by writing f as a function of t, and then just taking the derivative. F as a function of t, and differentiating. So it's not too hard to write f as a function of t. We're just going to replace the x with cosine of t and the y with sine of t. So our f of x comma y equal to x squared e to the 3y becomes f of cosine of t sine of t equal to cosine of t squared times e to the 3 sine of t. I guess I should have written f of t here. So our f of t is equal to cosine of t squared times e to the 3 sine of t. All right, and now we're going to take the derivative using the product rule and the chain rule. So derivative, f prime of t. All right, the derivative of this first piece, the derivative of cosine squared is going to be 2 times cosine of t to the first times the derivative of cosine, which is negative sine of t, times the other stuff left alone, e to the 3 sine of t, plus, then you switch. You leave the cosine t squared alone, multiply by the derivative of e to the 3 sine t is e to the 3 sine t times the derivative of 3 sine t, which is 3 cosine t. Seems kind of awful. Or we can, I don't have quite enough room here, I feel like, or we can use a diagram. So B, get the right words, by using the chain rule. So we're going to write our function, or sorry, write our map. So our f depends on both x and y, with an x and y both depend on t. I should mention, we'll see in the next example, this is not the only kind of mapping. It's not always f depending on two things and then two things depending on one thing. Although it's a very typical situation, it's not the only situation by far. So then we're going to say, great, our df dt, those are d's, I know I said d's, I kind of wrote del's, should be equal to, okay, it's all the paths. I should say one more thing here. So the first path goes through x. So it's from f to x and from x to t. So whenever you go from f to x, the way you're going from f to x is by taking the derivative. So it's the partial derivative of f with respect to x multiplied by the partial derivative of x with respect to t. No, sorry, not, it's not partial, it's regular. It's a dx dt, not a del x del t. It's a del f del x though. Plus the other path from f to t. That's going to be del f del y multiplied by dy dt. I kind of think about this, and this is actually later on when we talk about the probability stuff at the very end of the quarter, when we talk about Bayes' rule or Bayes' formula, this idea of one path being you multiply all the things together and then you add and then you do the other path and you multiply the things on that path together, that idea kind of resurfaces. So looking at this actually is really helpful for this, I think, for the probability stuff we do at the very end. So then we're going to look, sorry, our function's way up there. So our del f del x is 2x times e to the 3y times our dx dt, the derivative of cosine is negative sine, plus our del f del y is x squared times the derivative e to the 3y is e to the 3y times 3, and our dy dt is the derivative of sine of t, which is cosine of t. Now, technically, we should finish this off and plug in what x and y are. But you can hopefully see that that's going to give us exactly the same thing as what we have up here, right? 2 times x, which is cosine, times negative sine, times e to the 3y, which is sine, plus cosine squared, which is x squared, times e to the 3y, which is e to the 3 sine of t, times 3 times cosine t. Exactly the same. Oh, sorry, my shadow there is terrible. But they are the same. So if you do it this way, though, you typically will get asked to write it in terms of the lowest level variable. So we really should then be like, okay, it's 2 cosine of t times e to the 3 sine of t times, I should have brought the negative out in front, negative sine of t plus cosine squared t e to the 3 sine of t times 3 times cosine of t. Same answer. Maybe written in slightly different order, but order of multiplication does not matter, right? Order of multiplication does not matter. unless you're multiplying matrices together. And then the order definitely matters. But I don't think we do a lot of multiplying matrices together when we do the matrix stuff, so I wouldn't stop that too much. All right, that's all there was for that one. That's the whole answer. And we're almost out of time. Let's see. Let me look at one more example real quick, and then we'll call it a day. Just to show you one of the other types of things that can happen. So let's say we had this situation where you have w as a function of x, y, and z, and we're given x equal to t to the fourth, y equal to 3 minus t, and z equal to 2 plus 6t. And then we're asked to find dw dt. And while you could do it the long way like we did before, you could write this. Oh, I didn't actually write the function. That was real smooth. So let's actually write the function here. Sorry, I just skipped right over it with my function is x times e to the y over z. Apologies. I meant to not like draw that so wonkily. There's our function. So we could do this the long way, where your function is t to the fourth times e to the 3 minus t over 2 plus 6t. But I really don't want to use the product rule and the chain rule and the quotient rule all in the same thing. It's terrible. So we're going to do this the chain rule way, where w depends on x, y, and z, and x, y, and z all depend on t. So when we write dw dt, we're going to have three paths added together. Our del w del x times dx dt, plus our del w del y times our dy dt, plus our del w del z times our dz dt. Then we just go. So our function, just in case you can't see it right, it's x e to the y over z. Or I might write it as w equal to x times e to the y times z to the minus 1, just to make it easier to take the derivative of. So the partial of w with respect to x is going to be 1 times e to the y z to the negative 1, multiplied by my dx dt, which is 4t cubed, plus del w del y, the x is going to hang out. The derivative of e to the y is e to the negative 1, or as I always say in my head, the derivative of e to the stuff is e to the stuff times the derivative of that stuff. And the derivative of this stuff with respect to y is 1 times e to the negative first. You don't really need the 1 there, but I wrote it. Multiplied by dy dt, which is negative 1, plus del w del z, which is going to be pretty similar actually. The derivative of w with respect to z is also going to be x times e to the stuff times the derivative of the stuff. The e to the stuff is still e to the y z to the negative 1. But now the derivative of y times e to the negative 1 is going to be y times negative 1 times e to the negative 2, or negative y times e to the negative 2. And then dz dt is 6. I'm not going to do it because it's terrible, but then to finish this problem off, you would plug in t to the fourth for every x, 3 minus t for every y, and 2 plus 6t for every z, which is terrible. All right. Sure. It's close enough. I don't need to torture you with more. So that's definitely what you should be seeing in class tomorrow. If right, you didn't talk about the chain rule yet, right? So I imagine that's what we'll be seeing in class tomorrow. And then when we meet again on Thursday, we'll continue talking about the chain rule. We'll talk about a few other things, and then we'll move on to probably directional derivatives, I think is what's coming up next. Yeah, I think. Yeah. So mentally preparing for directional derivatives, you should definitely remind yourself of how the dot product works. So when you have two vectors, in fact, actually, let me use my last 2 minutes to say that. So just as a reminder, when you're finding the dot product of two vectors, so if you have something like, for example, u equal to the vector 4 comma negative 3 and v equal to the vector 2 comma 5, there's the easy way of calculating the dot product, which is where you say, okay, u dot v or v dot u, doesn't matter what order you write the dot product in, You're just multiplying the corresponding components together and adding up the result. So it's 4 times 2 plus negative 3 times 5, which in this case happens to be what, 8 minus 15, which is negative 7. You say one other thing, then you're free to go. I will also remind you that there's an alternative way of calculating the dot product, but it's not very good in that it's hard to calculate because you have to know the angle between the vectors. So if you drew these two vectors, I don't know the angle between them. Just to point out, U looks like over 4 and down 3, so U is kind of like that. And V is over 2 and up 5. That's kind of what they look like. And U dot V, another way to think about calculating U dot V is it's the magnitude of U, or the length of U, times the length of V times cosine of the angle between the two vectors. And so actually you can use the dot product to find the angle between two vectors, which is actually kind of neat. But we definitely, although we don't calculate the dot product this way very often, we do use this expression to help us determine some things about how the vectors are related to each other. So it is, and actually this idea comes up when we start talking about the directional derivative and when the directional derivative is maximized. So we'll definitely going to see this again in the future. So yeah, just thought that seems like a good moment to say it. All right, now it's time. I should let you go. I'll see you all on Thursday.